All right, for homework number 9, the first problem says write the first 5 terms of the sequence. So they give us a formula here. So a sub 1 is equal to 3 to the first over 1 factorial. So that's just 3. And a sub 2 is equal to 3 squared over 2 factorial. So that's 9 over 2. The third term is 3 to the third over 3 factorial. That's 27 over 6. And that reduces, or you could say, this is 3 times 2 times 1. So you could also knock that down to 9 over, this is going to be 9 over 2 as well. And then a to the fourth is equal to 3 to the fourth over 4 factorial. 3 to the fourth is 81. 4 factorial, so that if 3 factorial is 6, 4 factorial is just 4 times 6, so 24. And let's see, does that reduce? Yes, we can reduce by 3 again. So divide by 3, 27 over 8. And the fifth term would be 3 to the fifth over 5 factorial. 81 times 3 is 3 to the fifth, so that's 243. 5 factorial is 120, or it's 24 times 5. And I should say, this does this divide by 3? Yes. So divide by 3, 81 over 40. And I don't think that will simplify any further. All right, next one, the nth term is negative 1/4 to the n. So the first term should be negative 1/4 to the first. So negative 1/4. The second term is negative 1/4 squared. 1/16. The third term is negative 1/4 to the third, so negative 1/64. The fourth term is negative 1/4 to the fourth, so this will be positive 1 over 256. And then the fifth term will be negative 1/4 to the fifth. That's negative 1 over, let's see, 256 times 4, so 24, 22, 1024. All right. Next problem. Write the first 5 terms of the recursively defined sequence. So they give us the first term as 3, and then this says a sub k plus 1 is equal to 2 times a sub k minus 1. So this just means the second term, I have the first term. The second term is equal to 2 times the first term minus 1. So 2 times the quantity 3 minus 1 is 4. All right, and then we want the first 5 terms. So the third term is 2 times a2 minus 1. So 2 times 4 minus 1. 2 times 3 is 6. Fourth term is going to be 2 times, I'm just going to put this in, 6 minus 1. 2 times 5 is 10. And the fifth term is going to be 2 times 10 minus 1. 2 times 9 is 18. All right. Match the sequence with this graph. The graphs are labeled A, B, C, and D, and the sequences are down here. So take a look at these sequences. The terms are approaching different values for A and C. So if I look for almost like horizontal asymptotes or limits at infinity, if I look at limits at infinity, this one is approaching a larger number. This is approaching 0, it looks like. So let's take a look at our equations. This limit as n approaches infinity of 10 over n plus 1, that's bottom heavy, so that's 0. Whereas number 16, the limit as n approaches infinity of 10 n over n plus 1, that's its high, so that's 10. So 16 has to be A, because those terms are approaching 10, it looks like. or they're getting there anyway. And then 15 has to be C, because those terms are approaching 0. And they're not alternating. The alternating, B and D, have to have a -1 to an n in them. And then if I look at 17, this will only ever be -1 or +1, so that matches the graph for D. And this 18 will be alternating, but as n increases, the values approach 0, so that matches B. Write the next two apparent terms of the sequence. Describe the pattern you use to find these terms. So describing the pattern, I'm going to assume that means like find a formula for the nth term. Maybe that's not what they meant, but looking at these, the first thing I think of is, can I add or subtract something to get to the next term? And if that doesn't work, can I multiply or divide by something to get to the next term? So this one looks like it's just +3 each time. Okay, so the next two apparent terms, if I add 3, are 14, add 3 again, 17. Describe the pattern as just, add 3, but what about if they ask us to come up with an nth term? So instead of just saying add 3 each time, how do you generate these terms? So to do this, you want to compare two values of n. So n is 1 when the term is 2. N is 2, the second term is 5, the third term is 8, and the fourth term is 11. And it's really the 8 and 11 and the 11 that kind of put this into perspective for me. If I multiply the n by 3, I get close to the number I have here. If I just multiply by 3 and subtract 1, I think that works for each of these. 3 times 1 is 3, minus 1 is 2. 3 times 2 is 6, minus 1 is 5. 3 times 3 is 9, minus 1 is 8. 3 times 4 is 12, minus 1 is 11. So 3 times n minus 1 will get you any term that you want. For the next one, I'm not adding or subtracting, but this looks to be like we're multiplying. So what do I need to multiply 1 by? Multiply by -3/2. And if I keep doing that, I do get to the next term. So the next two terms, if I multiply -27/8 times -3/2, nothing cancels. I get +81/16. And if I multiply that by -3/2, again, nothing cancels. I get -243/32. And I want to come up with a general term. So I always have to write down the values for n, just so I can see try to compare what's happening here. And when I have fractions, I usually try to come up with a formula for the top and the bottom separately. And then I can simplify it if I want to. So I'm noticing that the even terms are negative. So it's not just going to be -1 to the n. It'll be -1 to the n plus 1 or -1 to the n minus 1. So I'll decide that later. The numerators are definitely powers of 3. And it looks like we're like 1 ahead. So the first term is 3 to the 0. The second term is 3 to the first. The third term is 3 to the second. So I think we can say we have 3 to the n minus 1. And we could also make that -3 to the n minus 1, right? Because I was just saying to get the correct negative signs, like the second term, for example, when I plug in 2, I'm going to get -3 to the first, and that'll give me the -3 I need here. And when I plug in 3, I'm going to get -3 squared, which is +9. So I think this works if I put the -3 in parentheses. And then there are powers of 2 in the denominator, and they're one behind as well, 2 to the n minus 1. So we could say this is -3/2 to the n minus 1. And maybe I could have started there because I said multiply by -3/2 each time. So I probably could have just started with this as well. All right, simplify the ratio of factorials. So remember, factorials mean, like 11 factorial means 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4. So the rest of this is 8 factorial. So the fact that this is 8 times 7 times 6 times 5, that's going to cancel out with those two. So it's just 11 times 10 times 9. That's 110 times 9, and that's 990. If you don't have numbers, you're still starting with what you have, n plus 2, whatever that is, and then subtract 1 to get the next multiple. So n plus 2 minus 1 is n plus 1. Subtract 1, subtract 1, subtract 1. You can keep going until you get down to 1. And same here, you would have n times subtract 1 and minus 1 and minus 2, and you would keep going until you get down to 1. So all of those are going to cancel, and you'll just be left with n plus 2 times n plus 1. And you can leave it like that, or you can multiply it together. For this section, find the limit, if possible, of the sequence. So this means that we're taking the limit as n approaches infinity when they say that. The limit of the sequence means if there is a limit, it's the value that the terms are approaching. So the limit of 5n squared over n squared plus 2, that's a tie. Divides that to 5, so that limit exists. Those terms are approaching 5. For 36, the limit as n approaches infinity of 5 minus 1 over n squared, that's 5 minus 0, so that one's also 5. The limit as n approaches infinity. So this simplifies, the plus 1 doesn't matter as you start getting huge values of n. So this is practically the square root of n squared. So it's really like you're comparing 2n over n. So this limit is equal to 2. It's like a tie, 2n over the square root of n squared, because we ignore the constant terms. Same thing for this one. The limit as n approaches infinity of a sub n, it's the plus 4 doesn't matter as you start heading toward infinity. So 5n over n is what this would simplify to. So that's 5. For this one, the limit as n approaches infinity of the sine of 1 over n. So when you plug infinity in for n, you get sine of 0. And sine of 0 is equal to 0. And for this one, the limit as n approaches infinity of the cosine of 2 over n. Again, as we plug in infinity, we get the cosine of 0. And the cosine of 0 is equal to 1. Use a graphing utility for this one. Now, you do not have to be able to graph a sequence on the graphing or on the AP exam. You shouldn't have to change the mode of your calculator on your AP exam, but it is kind of cool to see this. So go ahead and press mode and switch to, we're normally in function mode, but switch to sequence. Press y equals and it'll look different. So now y equals looks like this. And I will say, I don't use this very much, so I don't know what all of this stuff necessarily is for. I could probably play around with it and guess, but I do know that we're going to type our sequence in here. And to do n plus 1 over n, you can still use the alpha y equals. You can still use the fraction key. Or if you don't use that, you need to use parentheses. Normally we would type in x plus 1, but look, if you hit x, it types it in as an n. So that's why there's a whole string of things there. Kind of cool. And then I don't have any like extra first term to plug in here. So I'm just going to zoom 6 and see. Yeah, so that's the graph that I got. So you can trace these. And it just tells you what each value is as you go through. So use the graph to make an inference about the convergence or divergence of the sequence. Verify your inference analytically, and if the sequence converges, find its limit. So this definitely seems like it's going somewhere, right? If we trace, I'm getting closer and closer to 1. All right, so I'm going to make an inference that the limit is 1. So I think I had this on my key. So do we think this limit is 1? And then there's not really much work to show here. So do this analytically. This again is a tie, rational expression with a tie. So yeah, this comes out to 1. The sequence converges. And again, when we say a sequence converges, we mean that the terms are approaching 1 value. Determine the convergence or divergence of the sequence given the nth term. If the sequence converges, find its limit. So the limit as n approaches infinity of 2 over n factorial, that's definitely 0. So this sequence converges. And that just means, I wrote this every time on my key. I'm not going to write it out here for the video, but that means that if we were to graph this, the terms would be approaching 0. For the next one, we have an alternating sequence. Now be careful with this because we had a theorem in our notes that said if you can show that the limit as n approaches infinity of a sub n, of the absolute value of a sub n equals 0, then the limit as n approaches infinity of a sub n equals 0. So this was for alternating pieces, but this is only true for 0. So I can't ignore the alternating piece here because this limit is not 0. This limit is 1. So the limit as n approaches infinity of, I can't ignore the negative, it's negative 1 to the n times n over n plus 1. This is not going to approach one single value. This is going to bounce back and forth eventually between negative 1 and positive 1. So it equals negative 1 plus or minus 1. So that means that this sequence diverges because there is not one single number that the terms are approaching. All right, for 51, the limit as n approaches infinity of 3n squared minus n plus 4 over 2n squared plus 1. It does not matter what the extra terms are. We're only looking at the leading terms, which have the same degree. It's a tie. So this is 3 over 2. So this sequence converges. Okay, now 53 was kind of tricky. This made me pause for a second because we might accidentally think that this is a factorial. And so at first I was thinking, oh, it's a factorial over an exponential. And we talked about how even if it's 2n to the n, a factorial would grow faster. But this is not a factorial because remember, factorials are starting at a number and then you multiply each number, each previous integer that comes after it until you get down to 1. You wouldn't skip values here. Also, if you actually calculate out 2n minus 1 factorial, like if you plug an n into that, say plug in 5 or something, you're not going to get 1 times 3 times 5 in the end. You're going to get values that are both positive and negative, and whatever, if I plug in 5, would that be? That would be 9 factorial, so that would turn into 9 times 8 times 7 times 6 times 5. So if this is not a factorial, that means that even if you're plugging in infinity, you're still just getting a number and then multiplying by everything that came before it. So this exponential would, this infinity to the infinity would grow way faster than just infinity times a bunch of constants is basically, I guess, what I'm saying there. So I don't have a lot of work to show for this. I can do, I think I might have done a round of L'Hopital's here. So if we do like 1 times 3 times 5 times whatever, it's true that that limit is infinity. And it's also true that the limit as n approaches infinity of 2n to the n would equal infinity. And that's not one of our indeterminate forms, infinity to the infinity. So what do we do? So we can try L'Hopital's method. So what if I took the derivative of 2n minus 1? So that would be, you would still have the 1 times 3 times 5 times whatever. And then the derivative of 2n minus 1 would become 2. And because these are all constants, right, multiplying in. And then this derivative would become n times 2n to the n minus 1. So all of your n's are in the denominator, and that limit comes out to 0. So you only have constants in the numerator, and you have your variables in the denominator. So that's definitely a weird one. It's kind of, I don't feel like I'm not explaining it very well. But yeah, if this said 2n minus 1 factorial, instead of showing you what the numbers are being multiplied out, that would be infinity. Okay, let's see. What's this one? So what would this limit be? As we approach infinity, you could break this up if it's easier to look at, or you could say, yeah, it's either going to be 2 over n or 0 over n. So either way, you're going to get 0 as the terms approach infinity. If I want to show this a bit more formally, I think I split this up. So let's say, sorry, false equivalence there. Let's say n, the limit as n approaches infinity of 1 over n plus the limit as n approaches infinity of negative 1 to the n over n. So this limit we know is 0. And because the absolute value of this expression was 0, the alternating is also 0. So we do get a limit for this, and it's equal to 0. I believe we had this in our notes. You can rewrite this as 3/4 to the n. So as long as the base number is not larger than 1, then this is an exponential decay graph, so it will approach 0. So the limit as n approaches infinity of 3/4 to the n, that's equal to 0. Doesn't matter how close to 1 the fraction is. If it's less than 1, then it's going to approach 0 in the end. Factorials on the top and the bottom, so expand these out as you try to do the limit. So what is n plus 1 factorial? It's n plus 1 times, subtract 1 from that, n, times n minus 1 times n minus 2, and again, that would carry on until you got to like times 1. And n factorial, that's what this is, right? N times n minus 1 times n minus 2. You don't have to show that. You can just say, you can say n plus 1 factorial is n plus 1 times n factorial. That would be great too if you just did that. So this comes out to n plus 1. Oh, and am I supposed to be saying converge, diverge? Oops, sorry. Okay, converges, 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 converges. All of these sequences are approaching one value. This converges to whatever n plus 1 is. And then what about this last one? So the limit as n approaches infinity of the sine of n over n. So we've talked about this before. The sine graph ranges from -1 to 1. So we know that sine n will be somewhere between -1 and 1. But n will approach infinity. Oh, my pen stopped working. The n in the denominator will approach infinity. So it doesn't matter if what you have on top, you have some sort of constant on top over infinity. So that's 0. So this sequence converges as well. All right, and then last couple here. Write an expression for the nth term. So find the pattern. There's more than one correct answer. So as long as the answer you give, as long as I can plug in n equals 1, 2, 3, and 4 into whatever you say it is and get these exact same terms, then that's a correct answer as well. Okay, so keeping that in mind, again, I try to just separate it out. So I'm going to go with the easy thing first. The top, the numerator, is just n. Okay, and then take a look at the numbers. Like 2 is n plus 1, and 3 is n plus 2. And that's for all of them. The bottom number is 1 higher times 2 higher. 1 higher times 2 higher. So it's n plus 1 times n plus 2. That's it. You don't have to FOIL it together. You can come up with some other patterns that might work as well, but that's what I'm going with. And then for this one, again, I would suggest always writing the n's up above so that you have something to compare them to. It's easier to look at. I never usually look at the first term because like this one doesn't really give me much to go off of, but pay attention to the other ones. Oh, whoops. And I skipped a term in there. My bad. N equals 1, 2, 3, 4, 5, 6. So let's see. We're going to have x to the n minus 1, right? Because if n is 3, x is squared. If n is 4, x is... If n is 1, x is to the 0. That's why there's no x on the first one. And then you will, the more we work in this chapter, recognize these as factorials. But this is 2 factorial, 3 factorial, 4 factorial, 5 factorial. So, and again, if that's 4 factorial, that's in the 5th term. This is 5 factorial, 6th term. So we have to the n minus 1 factorial. All right, and then what about the true false? You can see I have just a book that a previous student must have written in, so sorry about that. But let's see. If n is greater than 1, then n factorial would equal n times n minus 1 factorial. I think that's got to be true because that's what factorials are, right? N times n minus 1 times n minus 2, etc. So yeah, so n factorial is n times n minus 1 times n minus 2, all the way down to 1. And yeah, if you started here, yes, that is n minus 1 factorial. So that's true. They have if n is greater than 1 because, if n is 0, then you're going to have negative 1 factorial. And as far as I know, I know that we don't work with negative factorials. I don't even know if that's like a legal math thing or not. We could Google that. Okay. And then last one. If a sequence converges, then the same sequence divided by n will converge to 0. So converges just means approaches any number. But then if you take that convergent sequence, which is some constant, and you divide it by n, and n is approaching infinity, yeah, that makes sense to me. The limit as n approaches infinity of a sub n over n will equal some number over infinity, and yeah, you'll get 0. So that's true as well. All right, that finishes our first chapter 9 assignment. Please come into office hours if you have questions on any of this or if you want some extra practice.